Welcome to RF and millimeter wave IC design class, and we are continuing our lecture on Unit 3 matching networks. And in today's class, we will see about a specific matching network. We call it as L section match. Just to revise what we have done yesterday, we discussed about the need of passive impedance transformation. Need in the sense just to convert from low to high or high to low impedance, and which is very much essential when we need to match different circuit blocks in an RF transceiver. We discussed about the quality factor of network, and then later we saw about series to parallel conversion, and we obtained the formula for the conversion. Like if you convert the network from parallel to series or from series to parallel, how you can actually get the values of those components. So in that case, we equated series and parallel network, and we obtained the expression for the resistance and the capacitance for an RC network, and we summarize that in this form. In a similar way, if we do an effort to understand or to find the conversion formula between RL and RL series and RL parallel network, you will get the conversion formula what you're seeing on the right hand side of the screen. And so with that, we concluded yesterday's class, and we'll continue from here now. So in today's class, what we will see is we'll take an example. Take an example by considering a resistance, a pure resistance of say some few ohms, and how we can appropriately match or down convert that to another resistance if that is the need. All right. So, and at the end of the discussion, we'll come to something called as LC match, and we'll also see the simulation of this L section match, and how the impedance are transformed exactly. The real part of the impedance is exactly matched. All right. So those things we will see. So we will start by looking at we'll just start with the case. Let me just write it as case 1. All right. So I'll mention, I hope I'm audible. Please respond in the chat so that I'll know that you guys are listening to me. So my need is, so we are discussing about impedance transformation. So see, I have a resistance of value RL, and I want to convert this into a lower value. So now the resistance value is, now as of now we'll take it as RL, and if I want to convert that into a lower value, so can I get some response in the chat? Are you guys listening to me? All right, okay. So in order to convert this impedance, convert this resistance into a lower value, yeah, so from the previous formula discussion, we know that if you have the relation between RP and RS is of this form, so that means RS can be written as RP divided by QS square plus 1, and definitely Q is something which we always tend to have a large Q factor, or at least we can say Q factor much greater than 1. So if that is the case, if I want to convert a resistance from a high value to low value, definitely we need to do some parallel to series conversion. That is what I am trying to tell you from this formula. So I want to make the resistance low, I need to convert, I do some transformation from parallel to series. All right, so I'll explain in this way. So you have a resistance of value RL, and the need is I need to down convert. The requirement is to down convert this value. Sorry, it is not down convert. I need a downward impedance transformation. Right. So as I just suggested, the RL value can be lowered only if you do a conversion from parallel to series. So what I will do now is I'll introduce a matching network, or I'll introduce element here, and that element is a parallel capacitor, and I'm calling the capacitor value as C1. Right. So as we discussed in our previous class, we know that RC parallel RC can be converted into series RC, and in that case, definitely the resistance is going to have a smaller value than the original resistance value of RL. Right. So that is possible with this by addition of this capacitor. But if our requirement is to have a purely resistive component, now this capacitance also will provide some impedance. So if you need only the real part, or if you need only the purely resistance part, then we need to cancel the effect of this capacitance. For that, we need to add another element here. So I'm adding actually an inductor to cancel the effect of this capacitor, because we know that the impedances of both will get cancelled or can get cancelled at a specific frequency, or if we operate those the circuit at resonance. Right. This is what I have drawn the circuit. Did I make it clear? So I started with the resistance RL. The need is to downward transform the impedance, or to just reduce the value of this RL to a low value to match a specific need. For that, first I added a capacitance C1 with the understanding that if I do parallel to series transformation, resistance value can be lowered from our previous day's discussion. Then in order to cancel the effect of capacitance, I also added an inductor, and I named that inductor as L1. All right. So what I can see from this side is, if I measure impedance at this point, what I exactly needed is, what I want at this point is RL should transform to a low value, and that impedance should be real. Only real part should be there. Right. This is my need. This is my requirement. So how will I further look upon this specific circuit? I can do transformation as I mentioned before. So first what I will do is I look at this R and C, which are in parallel, that can be converted into a series RC, right? So let me do this transformation here. So I have the inductance L, then I'm doing series to parallel transformation. So I have C and then R in series to that. So I'll be marking that in this form. So L1 will retain the same value. I need to find the value of capacitance C and in the capacitance as well as the resistance here. All right. So since we are converting into series, I'm just marking this resistance as RS. And capacitance, from the previous discussion, we saw that if Q factor is high, almost the capacitance value in parallel and series circuit are equal. For that reason, I'll retain this value as C1 itself. And RS is RP divided by Q square plus 1. Anyway, that again depends on the value of Q factor. Right. But one thing we know for sure, that if I can operate or at one specific frequency, that is at the resonance frequency, the real part of the impedance will be equal to RS. Right. Series. This is basically a series RLC network. So at resonance, the impedance will be equal to the resistive component, right? So this is what exactly we wanted. So if I want to transform a impedance from a high value, say RL, to a low value RS, I have done this transformation here. So let me explain this little more. How we can, okay, so now if I want to do this transformation, I need to properly choose a value of C and also to choose a value of L. So we will see that. But before that, if you have any questions, you can ask now. Is this clear what I'm doing here? Any questions on this? Are there any questions? If no, you can write no in the chat. Okay, yeah. So if you look at this, the components what I have added, one inductor and one capacitor in order to downward transform the impedance. This is of the form of an L, and that is why we call this kind of match as L match, right? So we call this as an L match. Adding an inductor and a capacitor, we call this as an L match. So now if I want to design an L match, I should carefully choose the values of L1 and C1 such that at resonant frequency or at the operating frequency, the impedance should be only real part, and that should be equal to a low value. So for that, let me first write what is the impedance of this network first, Zin. So if I look at Zin of this original network, I'm trying to do with the first network itself. So the Zin can be written as R and C are in parallel. So I can write it as RL parallel to 1 by S C1, or it is equal to RL divided by 1 plus J omega C1 into RL. That is the impedance seen from here of this R and C in parallel. And plus you have a series inductance. So I should write it as J omega L1. This is the impedance. Now the need is the real part should be equal to a resistance value or a pure resistance. That is our need, right? So let me write only the real part of this impedance Zin. So what should be the imaginary part? Imaginary part should be equal to 0. So from those two conditions, we are trying to uh, get the equations such that we can design or we can choose the values of LC, and of course the RS value, right? So the requirement is real part of the impedance I'll write, and from that I'll get the value, and imaginary part should be equal to 0. So if I write the real part of the impedance of this by just taking LCM for the above equation, I can write the real part as, or maybe I'll write in this form, RL plus J omega L1 into 1 plus J omega C1 RL divided by 1 plus J omega C1 RL is the expression. Now this is the expression what I have. Now I need to write only the real part of, I'm just considering only the real part of the impedance. So if I write the real part from the numerator, I'll get RL, and one more term I'll get, which is equal to, okay, so let me write that fully, RL plus J omega L1 minus omega square into RL C1 L1 in the numerator, and in the denominator I'll have 1 plus J omega C1 into RL. This is uh, this is what I have. Now I'll just multiply with the uh, conjugate of the denominator. So it is 1 minus j omega c1 RL divided by 1 plus, sorry, I'll just multiply with this 1 minus j omega c1 into RL, and if I work on this, I'll get this as, in the numerator I'll have RL term. Okay, let me write that also fully. RL minus j omega c1 RL plus j omega L1 minus j square is minus, so it is plus omega square L1 RL C1, then minus omega square L1 RL C1, and finally you have uh, plus j into omega cube RL square C1 square L1. That is for the numerator, and the denominator you have 1 plus omega square RL square and C1 square. All right. Sorry. So this is actually the impedance Zin. Now, if I write the real part of the impedance from this, I can write the real part as numerator. You have only one term because these two terms will get cancelled. All the other terms you have a j component. So RL divided by uh, 1 plus omega square RL square and C1 square is the real part of the impedance. Now, if I look at the denominator, specifically if I look at this factor, omega into RL into C1, you can identify that that is a Q factor of a parallel RC network of value RL C1. It is equal to QP is equal to omega RL C1. So I can write this equation further as RL divided by 1 plus QP square, right? So the real part of the impedance is exactly equal to RL by 1 plus QP square, which is basically the transformed value of the resistance when you do from parallel to series, right? That is the real part. Similarly, the observation here is what I can say. I hope you guys are following. What I can say here is RL is transformed into lower impedance by a factor of 1 plus QP square. That is the observation from the first calculation by looking at the real part of the impedance. Now we know that imaginary part should not be there, because what we need is a pure impedance, pure resistive impedance. So if I want to so if I want to make the imaginary part 0, then I should write we will set the imaginary part equal to 0. So by setting the imaginary part equal to 0, what I am doing is I'll get a condition such that I can choose the capacitance and inductance value, and that will definitely lead to 0 imaginary part. So what is the imaginary part here? Imaginary part, if I write, it is j omega L1 minus j omega C1 into RL plus j omega cube into RL square C1 square L1, and this should be equal to 0. All the imaginary terms should be equal to 0. Did I miss any term here? One second, let me check.
So that is RL square, the second term.
Oh yeah, minus j omega C1 into RL square, right? Thank you. So if I equate this to 0, I can actually eliminate this j omega term from all these. Then I'll be left with L1 minus C1 RL square plus omega minus C1 RL square plus omega square into RL square C1 square L1 is equal to 0. Or if I choose L1 outside, it is 1 plus omega square RL square C1 square equal to C1 into RL square, or L1 can be written as C1 RL square divided by 1 plus omega square RL square and C1 square. Similarly, how we wrote before, I can say L1 is equal to C1 RL square divided by 1 plus QP square. So what we got here is the real part of impedance is equal to RL by 1 plus QP square, which is a lower value, and the inductance should be selected in such a way that it should be equal to C1 RL square by 1 plus QP square. This is the real part of impedance and the inductance value. Now, say for example, if I'm assuming that the QP square value, if this is much larger than 1, I can approximate the real part of the impedance equal to, directly I can say, which is RL divided by QP square, and inductance value also can be written as C1 RL square divided by QP square. This is possible only if your Q factor is much larger than 1, or this can be further simplified as, by substituting the value of Q factor, this can be further simplified as 1 by RL into C1 square into omega square, and this can be equated as 1 by C1 into omega square. Right, that is just by substituting the value of QP, which is already written at this point. So these are the values of L1, L1, the L1 should be selected in this way, and the real part of impedance will be of this particular formula, right? So what we have done is we have just tried out downward impedance transformation by using something called as L match. So just to make it more clear how this matching network works, let us just take an example. So I can answer questions if you have soon after doing this question. So just try out this question. Design a matching network. Design a matching network to transform RL equal to 50 ohms to 25 ohms at a center frequency of 5 gigahertz. So at 5 gigahertz, uh, an RL value which is a 50 should be seen as 25 ohms. We need to choose the components accordingly. As we have discussed, only one matching network as L section, you can directly take L section match. So this is what we need to design to get the value of L1 and this C1, and this is RL which is equal to 50 ohms. So how will you go about this? We have the ready formula here, what we have discussed so far. So RL can be, the real part of impedance should be equal to this value, right? So I can directly write that real part of the impedance should be equal to 1 by RL C1 square into omega square. We will get the value for that because RL value is given, omega value is given, and we know what should be the real part of the impedance after by using this matching network. Similarly, L1 value can also be obtained by this value 1 by C1 into omega square. There also omega is known and C1 you will get from the first equation. So, and the formula what I have used now, the real part of impedance and L1 is on the assumption that the Q factor is much larger than 1. Let us see how that assumption works. So, can I get the values of C1 and L1 if you assume that the Q factor is much larger than 1? Yeah, so there are important things to understand from this question. So, one thing is the center frequency. So you will get to know what is the center frequency here, the operating frequency. Another thing is it is given that RL should be transformed from 50 to 25. That means this is sometimes called as a transformation ratio. Transformation ratio, and transformation ratio in this case is 2 because we have to convert from 50 to 25. Transformation ratio is 2 in this case. All right, so we'll talk about that further. Now, what values you are getting if you assume that the Q factor is much larger than 1? So this should give you the value for C1, and from here you will get the value for L1. Can I get answers in the chat? Yes, Dinesh, you got C1 as 0.9 picofarad. Yes. And what about L1? So with 0.9 picofarad, substituting at omega of 2 pi into 5 gigahertz, what is the inductance value? Any answers for that? Shri Nikhil, are you there? Yes, it is 1.12 nanofarad. So you will get L value as 1.12 nano Henry. That is L1 value. But we didn't verify whether, yeah, it is 1.125 nano Henry, right? So, but we didn't verify whether the Q factor of this is much larger than 1 so that we can assume these values. So how will I verify the Q factor? Q factor can be verified as different ways we can verify. So now if I take the Q factor equation as RL into C1 into omega, and if I substitute the values here, if you do this calculation, I think you will get it very close to 1.413. Right, the Q factor is only 1.413. That means the QP square, which is much greater than 1 assumption, is not valid in this case, because we have selected the value of this one. These two equations we have selected based on the assumption that QP square is much larger than 1. Yes, Dinesh, it is 1.413. So this is not valid now. So this is not valid. So if this is not valid, then we should um, find the actual value. So I could have directly calculated that, but just to tell you guys that if you are simply assuming, that could lead to error in the result. So now what we should do is we should go with the exact expression. So the real part of impedance should be equal to RL divided by 1 plus QP square, and that will give you a different value of C1, and with that I can take L1 value as RL square C1 divided by 1 plus QP square. That will give you another value of L1. If you are getting those values, please put in the chat box, so that our final circuit will be something like this. So this is a 50 ohms, and what I want to see from here is 25 ohms purely resistive component. So what are the new values of C1 and R1? Any answers for that? New value of C1 and R1? Alright, so please let me know the value of C1 and R1. Yeah, so one more way how you can verify the Q factor is directly, because we know that roughly your RP is equal to, RP value will be equal to QP square into RS. This is what roughly we can say. Again, here also we are making that assumption, but still that is valid here. So QP is basically equal to under root of RP by RS. So in our case, RP is 50 and RS is 25, which is equal to root 2, which is 1.414. That means your Q factor is very, very less. So directly you can go with the the equation. No need to apply mm, any what to say, assumption of Q factor is small or something like that. You can always verify Q factor and then you can go ahead with the design. And if you do this, can I get the answers for C1 and L1? Are you guys there? So what are the values of C1 and L1? Usha, are you there? Usha. Virupakshi,
Sir, I'm doing.
Yatish,
Yes, sir, I'm doing so.
how long it will take, no, just to find the value of C? Sushan, 96.7 femto. I think that is not the right answer. Maybe you can check Sushan again. Yeah, it is 0.636. 0.636 picofarad, and if you substitute that, you will get the L1 value. I'm writing the answer here. This 0.796 nanohenry. So these are the answers for L1 and C1. And with this, if you if for with this values, if you simulate, so 0.636 pico and 0.796 nano, if you do that, you will definitely we are supposed to get a value close to 25 ohms, right? So we'll quickly verify this specific design in our cadence. So I'll share you the screen now. Now we'll verify this with cadence and see whether these are matching or not. All right. So can you guys see the screen? All right, yeah. So what we do now is what you can see on the screen is the same LC match. I have a 50 ohm resistance here, and I have connected the initial value, which is 900 femto, 0.9 pico, and this 1.12 nano here. I have set up the circuit over here, and I have selected. Yeah, I have just set the frequency resistance values as usual, and I'll show you the test bench, the setup here. Yeah, so I have enabled an SP analysis. SP analysis basically give you all the all the parameters. Basically, you can go for S parameter analysis, Y, Z, all the parameters are available from this. So I have set the operating frequency as 5 giga, then the input input signal level as minus 20 dBm, and I have set up this window here. Yeah, so I have selected the port. I am sweeping the variable from 1 giga to 10 giga, and the analysis which need to be enabled is this ESP analysis. So that I have done, and I'm just simulating this. Just saving and simulating this again. So the values what you're seeing on the circuit schematic now is based on the assumption of Q factor. That Q factor is much larger than 1. So we wanted to transform the 50 ohm to 25, but let us see what impedance we are getting. Whether the imaginary part is cancelling, imaginary part is 0 and the real part is 25, we'll just check. So I'm going to the main form, and in the main form I'm going to SP Z parameters here,
I'm first clicking the real part, and then I'm changing this to append, and then clicking the imaginary part, and I'm just, yeah. So what you're seeing on the screen now is the result of this. So let me keep a tracer here, and if you move this tracer to close to 5 giga, yeah. Anyway, yeah, this is 5 giga, and you can read the result on the screen. I hope you can see the result. The red line, what you are seeing, the impedance is 16.676. But what we need is, or what we are designing is for 25 ohm impedance, and there is a significant imaginary component present. The imaginary component is not zero or very close to zero or smaller than zero. You can see that 16 ohm is the real part impedance and 11.6 is the imaginary part, which is not the intended value, right? So what we will do now is we will just go back. I'll just close this window. We'll go back. We'll change the component with the new component values after realizing that the Q factor is not much larger than 1. So I'll give the new value here. The new value is 0.796 nanohenry that I have given, and for the capacitor the new value is close to 0.636. So 0.636 pico. That also can be written in terms of femto, right? So I just saved it and I'm analyzing this. All right. I'll go to results in the main form. I'm going to plot again, changing to replace. First, I'll plot the real. Then I'll change this to append, and then I'll plot imaginary. And if I give OK, I should get the new window here. I hope you can see the window. Let me just change the background color so that you can see that properly. All right. Now you can see again the cursor is exactly at 5 giga, and yeah, you can see that the impedance at 5 giga is yeah, you can read the impedance value even on the left hand side. 25.025 is the real part, and the imaginary part is very close to 8.411 milli, which is lesser than, it is very close. We can consider that it is very close to zero, right? So these are the, I think I will change a bit. Yeah. So now we can read it. 25.02 is the ohm. That is what the intended the resistive component, and the imaginary part is 8.4 milli. All right. So this is a simple simulation of an L section network, and these kind of networks are these kind of matching networks are widely used, especially when we talk about a low noise amplifier, where we need to have a input impedance of 50 ohm in order to match with the antenna impedance of 50. We generally use this kind of L section network, but as an off-shift component, mostly in order to reduce the noise figure from the noise figure of the LNA part. All right, so this is all about today's class. If you have any questions, I can take questions. Otherwise, we'll wind up now and we'll continue from next week.